Guys, welcome. So today we're gonna continue with our adventure in integral calculus. Well, I will talk about a very important topic today, which is called the mean value theorem for integrals, just like I said yesterday. And we will be talking about the average value as well. So let's get started. Today's lecture is going to be a shorter one. You will see also a bunch of applications as well. All right, so today we'll talk about the mean value theorem. For integrals. And this is a very important topic, and it's done even not just in Calculus 1, but also in any introduction to analysis course. Well, if you want to go more in depth about this, to see more theoretical stuff about this mean value theorem. And the statement goes like this. So I'm just going to, call this a theorem. And the statement is the following. If f is a continuous function on a closed interval on the interval AB, and like I said, this is a closed interval AB, right? Okay. Then there exists at least, and this is important, at least one number C and this C will be between A and B. Let's write like this in words, between A and B, such that the following formula holds true. And the formula is the following. So the integral from A to B of f of x dx will be just b minus a times f of c. So this will hold true for some value c between a and b. Okay, so this is the mean value theorem. Well, let me point out a remark here. Well, if you look at the formula, and if you write this, so let's point out this remark. By the fundamental theorem of calculus, we know that the integral from a to b of f of x dx is nothing else than just f of b minus f of a. Well, where capital F is the antiderivative. So f prime of x is f of x. Okay, right? So so the mean value theorem, and let's just call this mean MVT for integrals, can be restated as well. You can restate it in the following way: f of b minus f of a, so capital over b minus a, is nothing else than just f of c. But you know this is f prime of c. So this, as you can see, this is nothing else than just the classical mean value theorem applied for the antiderivative, right? So keep in mind that the antiderivative is nothing else that that this function, capital F, whose derivative will give me the initial function f of x, right? All right. So with this in mind, we'll let's do some applications. We will see that we will provide some applications even in physics. Anyway, let's get let's present some application. But first, I would like to start with an example. Example 1, let's say. All right. But in fact, no, wait, before that, I want to explain a bit the geometric meaning. So let me just draw a graph. So imagine we have something like this, that the graph of the function is something like this, right? Y equals f of x. And suppose that this function is defined on this interval, a and b, right? And well, guess what? There exists a point C here between A and B, such that it will correspond on a, let's say, average value on the graph of this. This is what's going to happen. You will see that we will call this number 1 over b minus a times the integral of a to b of f of x dx. We will call this the average number of f. Anyway, we'll get there. All right, now let me do an example. So the first example is the following. We want to find the value, so find a value. Oops. So find a value of C guaranteed by the mean value theorem. Okay, let me write in words. But from now on, I will abbreviate mean value theorem for integrals as MVT. So the mean value theorem for integrals for this function f of x is sine of x on 0 pi. Okay? All right, let's see. So we have this function. Right? F of x equals sine of x. So we would like to, we want to find that value C, as you can see here. So we want to find this value, which is guaranteed by the mean value theorem for integrals and for this function. So in other words, what we need to do is and also keep in mind that we want to apply the mean value theorem on the interval 0 pi. So what we need to do at this point is to compute the integral of sine of x. So we will start with this integral, the integral from 0 to pi of sine of x dx. Right? This is a continuous function on 0 pi. I have no problems. Well, you know that this is nothing other than just negative cosine of x from 0 to pi, right? Because negative cosine is the antiderivative of the sine, and this would be nothing else than just negative cosine of pi plus cosine of 0, which will be minus negative 1 plus negative 1. And this would be a plus 1, sorry. And this would be 2. So this is the value of this integral. So let's keep this in mind. And now what we would like to do is to apply the mean value theorem. So by the mean value theorem, so by applying the mean value theorem for integrals and keep in mind, let's go back to the mean value theorem. As you can see, I have the integral from a to b, but in our case, we have the function is defined on 0 pi, so we will have a is 0 and b is pi, with a 0 and b pi, right? It follows that the integral from 0 to pi of sine of x dx is, well, as you can see, is f of this number c times pi minus 0, which will be nothing else than just pi times f of c. Okay, but this integral, we know that this guy here, as we compute it, is equal to 2, right? This is 2. So finally, this would give us it will give us what? 2 equals pi f of c, right? This is for some c, I forgot to say here, for some c in 0 pi, and again, for some c in 0 pi. So this finally gives us, so f of c sine of c, so sine of c equals 2 over pi, which will be equivalent with saying that c is nothing else than a sine inverse or arcsine, whatever, of 2 over pi. And this is approximately, if you want to plug it into a calculator, if you want to compute it, this would be this would be 0.69. Anyway, now let's draw a graph. So this is how you solve, how you apply the mean value theorem for integrals in this case. And now let me just draw a picture so that you can see clearly. So let's just say, so here we have 0 and pi. Let's say we have pi here. So the function goes like this, right? And at some point here, 0.69, this is c is approximately this guy. You'll have here a point, f of c, on the graph of y equals cosine of x, right? So this is what will happen. All right, now let's provide some applications of the mean value theorem for integrals. And before I start doing this, let me just tell you something, because I talked a bit about the average value of a function. So now I would like to say a few things about the modeling the average value of a function. Okay. All right. So if we consider, so if f is a continuous function, on interval AB, then the average value right, of f on the interval, on the given, on this interval, let's say, is given by the integral, and will be given by the following integral. So we'll call this AV from average value. So this would be nothing else than just 1 over b minus a times the integral from a to b of f of x dx. So this is the average value of a function f. In fact, let me put it like this so that it's even clearer. So A, V, and let's see here f of f. So the average value of f is nothing else than just 1 over b minus a times the integral from a to b of f of x dx. Now let's see a quick example. And of course, this average value of f will correspond to some point in AB of f of that point for some point in AB. Anyway, as we know from the mean value theorem for integrals. All right, now let's see an example. I forget the number, but anyway, find the average of, and let me take the simplest parabola, f of x equals x squared on, let's say the interval, let's say 1, 5. So we'd like to find the average of this. So as you can see, the formula above, so the average so from the formula above, the average of f is nothing else than just 1 over, and in our case we identify, so a is 1, b is 5, so it's 1 over 5 minus 1 times the integral from 1 to 5 of f of x dx, which in our case, f of x is nothing else than just x squared. So we're going to replace this here. We have x squared dx. So this would be 1 over 4 times the integral from 1 to 5 of x squared dx. Right? So this would be 1/4 times the integral of x squared is x to the cubed over 3 from 1 to 5, which will be nothing else than just 1/4 times 5 cubed over 3 minus 1 cubed over 3. And this would be 112 times 124, right? 125 minus 1. And this would be 124 over 12. And this would be okay, 4. So it will be 32 over 3. And all right, whatever this is. So I'm just going to leave it as a fraction, right? So this is how we find the average value of a function f. All right. Now I want to go towards, I want to veer towards applications, and I will have in mind the following. So let's do the following example. So another example. All right, let's see. All right. So now this example will have in mind about the modeling average speed of traffic. This is like a real world application. All right. So the problem states the following. So suppose okay, suppose a study suggests that between the hours of 1 p.m. sharp and 4 p.m., right? So between these two, on a normal weekday, right? The speed of the traffic at a certain expressway, at a certain expressway exit is modeled by the formula. So the formula is given by, let's say, S of t, and we're gonna, this will be a cubic polynomial. So this is st cubed minus 21t squared plus 60t plus 20. So it's modeled by the formula S of t kilometers per hour. Well, usually it's miles per hour here in the US. But anyway, let's stick to the European way, kilometers per hour, where t, as you can imagine, is nothing else that it's is the number, and this is important, the number of hours past noon. So this will be a very important information. All right. Anyway, we'll get to it. All right. So we want to compute the average speed right? The average speed of the traffic between the hours of 1 p.m. and 4 p.m. Again, the average speed of the traffic between these 2 hours. All right, let's look at the problem again. All right, so you see the speed of the traffic on a normal weekday is modeled by this formula. So it is modeled by this cubic polynomial. And T is the number of hours past noon. This is important. So what will be the goal here? If you analyze the problem carefully, so you have this function here, right? And if you look at the problem carefully, basically, what will be the goal here? So I want you to read it very, very carefully. And you will see that the goal here is nothing else than just to find the average of my cubic function. So we would like to find the average of S of t on the interval 1, 4, right? Where the interval is given by those 2 hours, as you can see here, 1 p.m. and 4 p.m. Because it says quite clearly what we want to compute. We want to compute the average speed. And the average value of our function S of t will be nothing else than just the integral between those 2 hours of my function S of t, which is nothing else than the speed of traffic, right? All right, so let's say this. So the goal, this is important, is to find the average of S of t on the interval, and the interval just denoted, so 1 p.m. I'll denote it by 1 and 4 p.m. by 4, so this would be 1/4. So that's what we need to find. So what is the average of f? So we know that the average, let's say AV of s, of our function s, will be nothing else than just, okay, let me, 1/4 minus 1 times the integral from 1 to 4 of s of t dt. So that's, we know this. Okay. All right, so let's compute this. We know who s of t is, so we just plug it in. So the average value of s is nothing else than just 1/3, right? Times the integral from 1 to 4 of, and now we're just going to plug in the function. So the function was given by 2t cubed minus 21t squared plus 60t plus 20, I think, yes, plus 20 dt. All right. Oh my. And now we're going to apply the basic properties of the integral. So this would be, so the sum rule for integrals, this would, by applying that, this will give us 1/3 the integral from 1 to 4 of 2t cubed dt minus the integral from 1 to 4 of 21t squared plus the integral from 1 to 4 of 60t plus the integral of 20 dt. All right. Now we're going to take the constants out. So this would be equal to 1/3. So this would be 2 times this integral minus 21 times this integral plus 60 times this integral plus 20 times this integral. Oh my. So we have a bunch of them to compute, right? So this would be equal to 1/3 times 2 times, this guy will be t to the 4th over 4 from 1 to 4 minus 21 times t cubed over 3 from 1 to 4 plus 60 times t squared over 2 from 1 to 4, and the last one plus 20 times t from 1 to 4. And now we do all these computations, all this algebra here. So this would be 1/3 times. So this would be here okay. Okay, so it will be 1/2 from 256 minus 1 minus, here will be 7 times 64 minus 1 plus 30 times 16 minus 1 plus 20 times 3. And this would give us, if you, okay, if you want to go further with the computations, this would be nothing else than just 1/3, 1/3 times. So this would be 255 over 2 minus 63 times 7. 441, I think, plus this guy is 450 plus 60. And this would give us over 6 over 3, so 190. Okay, so it will be 1/3 times 196 times 5. And this would be 65.5. Okay, so that is the average value. All right, 65.5. All right, as you can see, the only thing we did is just to apply this formula on this interval 1/4. So that's what you need to do. It's nothing, not a big deal. That's it. All right, now I would like to do another example, another application, and this time we would like to model not just the traffic, the speed of the traffic. We'd like to model the average temperature. So let's see another example. So here we'll be modeling modeling the average temperature. All right. So suppose that during a typical winter day, in a city, the temperature and again, I'm going to consider in degrees Celsius, not Fahrenheit. The temperature X hours after midnight right, is modeled by the formula so the formula is given by, let's say, T of X is equal to, so 2 minus 1 over 7 times X minus 13, everything squared. So it's this formula. And now what we're interested to do here is the following. So we would like to find the average temperature over the time period from, let's say, 2 p.m. to 2 a.m. to 2 p.m. and find a time when the average temperature actually occurs, when the average temperature actually occurs. Okay. All right, so let's see. See, X hours, so the temperature X hours after midnight is given by this formula here. So we have this function, which is a quadratic function. So you know how to compute basically everything about quadratic functions. And we're interested to find the average temperature. Well, when you hear this word, you know what to think of. And this is between these 2 hours, between 2 a.m. and 2 p.m. This is important. Pay attention, because we would like to identify these two with some numbers. Well, you'll be tempted to say, well, maybe I should identify with 2 and 2, but it doesn't work that way. So if you start from 0 at midnight and 2 a.m. will be 2, then 2 p.m. will be not quite 2. It will be maybe something else. Maybe it will be 14. So pay attention to this detail. And also, we'd like to find a time, and this is important, when the average temperature actually happens. All right. So let's get going. All right. So we have this function, right? So we know that T of X is 2 minus 1 over 7 times X minus 13, everything squared. And the average value, AV of T, as we know from the formula, will be nothing else than 1 over, pay attention now, 14 minus 2, right? Because it says 2 hours after midnight, you see? So it models, I want you to look very, very carefully, because it says here, it says clearly it's X hour after midnight. So this is how we proceed. So at 0, it will be midnight. At x equals, so at x equals 0, it is midnight. At x equals 2 will be 2 a.m. And then at x equals 14, it will be 2 p.m. So I want you to be very careful with this. That's why we put the average, the bounds of the integral. So you will have something like this here, will be 2 and 14, right? Of t of x dx, which will be nothing else than 1 over 12 times the integral from 2 to 14 of t of x dx. Okay, and now what we need to do at this point is just to compute this, this thing here, right? So we need to compute this mess. So let's do it. So the average value of t, like I said, this is 112 times this integral from 2 to 14 of t of x dx, and this would be equal to 1 over 12 times the integral from 2 to 14, and now let's plug it in. So this would be 2 minus 1 over 7 x minus 13 everything squared dx. So this is how it would look like. And now if you go further, so this would be 1 over 12. Oh my, let's do it. Times this integral from 2 to 14. Okay, I'm going to write like this. So it's 2 dx minus the integral from 2 to 14 of 1 over 7 times x minus 13 everything squared dx. And this would be 1 over 12 times, here I'll take the 2 outside, so this would be the integral from 2 to 14 dx minus, minus 1 over 7, the integral from 2 to 14 of x minus 13 squared dx. Okay, and we keep going, and this would be equal to 112 times this guy here is 2 times x from 2 to 14 minus 1 over 7, and we're going to leave this integral like this. We're going to do something to it at some point. Well, you'll see what. And this would be equal to 1 over 12 times, this would be 24 minus 1 over 7, this integral. And now what we need to do is just to take care of this integral here. So we're left with this integral, and we need to take care of it. So what should we do? Well, like I said, even in yesterday's lecture, you can expand it, right? You can easily expand that x minus 13 squared, right, with the formula. You can easily do that, but I prefer to stay in tone with what we have done yesterday, and we learned about the integration by substitution. So we would like to do that. So next, we compute the integral. Let's call this I, is from 2 to 14 of x minus 13 squared dx. Okay, and the way we're going to do this, we're going to use the u sub. So let u be x minus 13. So from here, du is dx, right? So I have no problems. And now let's be careful with the bounds. When x equals 2, u will be what? U will be negative 11. And when x equals 14, u will be 1. Okay. So the integral, let's call this I, will be, and now I'm going to change the bounds. So this would be what? This would be the integral from negative 11 to 1 of u squared du, which will be nothing else than just u cubed over 3 from negative 11 to 1. And this would be equal to 1/3 times 1 over 3 minus 11 cubed over 3. Oh, sorry. Which will give us, it will be 1 over 3 minus 11. So it will be 1 minus 1,000, yes, over 3. All right, so this is the value of this integral, right? Let's keep this in mind. And now I would like to go back. So finally, so the average value of t will be nothing else than just 1 over 12 times 24 minus 1, because it was 1 over 7, so 1 over 21 times 1 minus 1,331. And this would be equal to, my God, this would be, all right, let's do it. So it's 112 times 1 over, no. So this would be, anyway, let me just do it by calculator. All right, so this would give us, so it will be, at some point, will be negative 23. Well, after some computations here, I'll leave this to you as an exercise. So this will be negative 23 over 3, which is approximately, let's say, negative 3.3 Celsius. So it's quite cold, I would say. Well, you still can survive at this temperature. Oh, what did I do? Sorry about that. You still can survive at this temperature, but it's pretty cold. So probably, I don't think we had this winter anything like this in Lubbock. All right, now what I would like to say is that the average, so keep in mind that we have something else. So we would like to find a time when the average temperature actually occurs. So we will say that the average temperature right, is equal to the temperature at time x, right? So that's what we need to know. All right, then here I think it's over 7, not over 3, sorry about that. All right, now we're gonna have the following. So this implies that negative 23 over 7, it will be equal to the temperature at the time x, which will be T of x, right? So this is this guy here is T of x. So this would be, we will set equal the average temperature, which we find, so AAV of T. So this guy is the average temperature, so this would be equal to T of x. So this would imply that negative 23 over 7 will be equal to 2 minus 1 over 7 times x minus 13, everything squared. And once we do some algebra here, some elementary algebra, this would be nothing else than just 23 times negative 23 times 14 minus x minus 13, everything squared, right? And this would be equivalent with, if you want, with x minus 13 everything squared is nothing else than just 37. Or if you want, this is we can say that x minus 13 is plus minus square root of 37. And this would be equivalent with x is 13 plus minus square root of 37. And that's it. And we're done. So this is a time when the average temperature actually occurs. Anyway, I'll let you plug in this number into a calculator and to see after what time x this will happen. All right, guys, I think this will sum up everything for this lecture. There will be another lecture where I'll be talking about some, just like I said yesterday, about some numerical integration formulas. This will be very important, especially when you deal with functions that cannot be computed. So basically, there will be some formulas, these quadrature formulas that will approximate the values of a certain functions. Anyway, that will be the last lecture. This is more like that lecture talking about these type of numerical integration type formulas will be more like a fantasy. It's not a requirement for the actual course. So anyway, but I'll do it anyway. So thank you very much. I think I will stop here.